Section 2.2, Forces. We will start the discussion with weight. When released in midair, objects can tend to fall to the ground. This is something that we always experience because of a force called gravity. On Earth, this gravitational force is constant. It can be modeled by a constant that we will describe later. So it seems that the Earth attracts objects to the surface. So this is a universal phenomenon, and it basically states that each object will attract every other object in the universe. But for now, we're going to be focusing on Earth, and thus we will be focusing on weight. So we will start by thinking about this somewhat empirically. So if we have some sort of mass, and we drop that mass, we let go of the mass, well, the mass is going to fall over due to the weight phenomena, and that should be no surprise to anybody. The mass will fall to the ground to a hard surface. And we will be talking about how this weight can be proportional to a mass. So if we have our weight, then that shift is going to be proportional to the mass. So we will call this weight the force due to gravity. And this is going to be proportional to the mass, the gravitational mass of some object. Well, now we have some issue because here we have force, which is a vector quantity. And we also have our mass, and our mass is a scalar quantity. So how do we reconcile this? Well, we have a place to put in a constant of proportionality. We have a place right here where we can insert a constant of proportionality, and we're going to call this constant of proportionality g. But this needs to be a vector so that this equation is satisfied. So our force, gravitational force, is equal to some vector g times the gravitational mass. So now we will discuss a principle of equivalence so that we can learn more about this gravitational equation here. So the principle of equation says that, the principle of equivalence says that empirically all objects will fall to the ground with the same acceleration. So what does this mean? So this means that if I have a feather, maybe a green feather, or maybe this is like I don't know. Yeah, this is a feather of a green bird. And then we also have a bowling ball. Maybe this is the type of bowling ball. I'm in Massachusetts, so here we have the bowling balls that don't have the holes in them, but we'll put the holes in them for the sake of example, so we know that this is a bowling ball. Here's a bowling ball. Let's say that it's 12 pounds. And, well, this feather is going to be a lot less than 12 pounds, but the principle of equivalence says that these should fall at the exact same acceleration. So that principle holds only in a vacuum. Outside of a vacuum, you need to reconcile air resistance. And, of course, because the bowling ball has much higher density than the feather, the bowling ball is going to fall faster. But if we sucked all of the air out of the room, there's a great video on this, but if you sucked all of the air out of the room and you dropped the feather in the bowling ball, they would fall at the exact same acceleration. I find that very interesting. So we have discussed that force equation here. So we have the gravitational force is equal to g times mg. Well, we're going to make this also equal to the inertial mass times the acceleration. So that's Newton's second law. So now we are going to take this here. So we have g times mg is equal to mia. Now we are going to solve for acceleration. So we get acceleration equals gmg over mi. And for the sake of simplicity, we are going to rewrite this as G times mg over mi. Now, the ratio here is going to be some scalar, so that's constant. And we can really set this equal to whatever we want. So we're going to let this equal 1. So thus we get the acceleration vector is equal to g. Okay. So g is thus the acceleration experienced by objects in free fall. So empirically we have measured g, so we're going to set a definition here. We have measured g such that g is about, or well, the magnitude of g, so I'll write it without a vector, is about 9.81 meters per second squared. That's consistent with the dimensions of acceleration, which is good. So we have some sort of relation between acceleration and force. Now, I would like to make an approximation. In physics, we like approximations, kind of. We are going to let this be about 10 meters per second. And on a test, you'll be very happy because then you'll have a nice number to work with, not that 9.81, so you don't need to do your calculator business. Okay, so essentially, to summarize what we just did, we stated Newton's second law, but we also said that the acceleration on Earth is g, which is about 9.81 meters per second squared, which we approximate to 10 meters per second squared. Okay, so now I want to change gears and I want to start talking about surface forces. So surface forces are important forces that kind of counteract the gravitational force, the weight force, right? So on the ground, objects do not go through other objects, right? So that's a fairly simple statement. But if I have a table, if I have like a table, then I have a block on the table, it is reasonable to assume that that block will not go through the table. But to this point, we have only discussed some little weight force here. And that's a problem because if we've only discussed the weight force, then it should be true that the block goes through the table. And luckily, that is not true because I'm drawing on my tablet right now and my tablet's on the table and it's not going through. So there's another force that we need to look at that counteracts this gravitational force. So now we will look at some other forces that counteract the weight. So when two objects are in contact, there's going to be a constant force between them. And there's, well, really going to be two forces, but they're going to be equal and opposite because of Newton's second law. That means that they're not breaking each other and they're not repelling each other, right? They're just contacting each other. So let's draw this a little bit. So we're going to have two bodies, kind of. So let's draw this out. Maybe here's body 1. And then we're going to have a plane tangent to body 1. Move that to make sure it's actually tangent. We're going to have another body here, body 2. Okay, so there's body 2. So these are both in contact at this little area here, at this black tangent line, tangent plane. This is like a cross section here. So this is going to be maybe y-axis, this is going to be x-axis, and maybe the z-axis points into the board. So these are three-dimensional objects, but they're in contact, and this is all we need to look at right now. But essentially, we can look at contact forces in the form of some normal force. So this normal force is going to be normal or perpendicular to that tangent plane. So here's the one normal force here. We'll call this force F sub n. And the way that we determine what the normal force is it is the force that is required such that these objects do not break one another. So that's how you calculate the normal force. It's very kind of strange, because we're going to impose that objects do not break in this introductory mechanics course. And then we can always decompose this normal force into its vertical component, the normal force, but we can also decompose it into some horizontal component. Say we have a horizontal component, and this will be called the frictional force, and we call this F sub F. So there's the frictional force. And then your normal force could be some decomposition or some sum of those forces. So maybe your normal force looks like that. But essentially, it's a decomposition or a superposition of the normal force and the frictional force, and that is the force that counteracts the weight. So it's the essentially the normal force is the one responsible for objects not penetrating each other. So we don't really have a first principles formula, as I said earlier, so it's whatever we need for it to not break. So let's try an example. I like doing examples in red, so we'll do this in red. So let's consider the let's consider somebody in an elevator ascending with an acceleration a. So let's draw this free body diagram. So we do free body diagrams when we're dealing dynamics. So there's our little particle. We have some normal force. We have some force due to gravity, which we call mg. And then we define some basis such that we have a unit vector, e hat sub y, pointing in the upwards direction. So now we're going to put this guy, we're going to put this little guy into an elevator. And there's this little guy in the elevator. And now we are going to add an acceleration to the whole system. So there's an acceleration. So now what we are going to do is we are going to look at Newton's second law. So the Newton's second law says that the sum of all forces, and we only have y direction, so forces in the y direction, but I'm not going to put the y index there because we don't really need it, is equal to the mass times the acceleration. So now we want to find the normal force. So we know that, well, we don't need to find the normal force. We're just going to put it into an equation. But the sum of forces, we know that we have some normal force. We also know that we have some mass times gravitational acceleration. So from the elevator point of view, in the elevator, we have our own F equals ma, and this is going to be n minus mg equals 0. Thus, our normal force, or well, I like putting the F there, is going to be equal to 0. Or, sorry, not going to be equal to 0. It's going to be equal to mg. So when we're in the elevator, without an acceleration going upwards, we have that the normal force is equal to mg. But now we need to find a new normal force, because now for the when we're looking at the whole system, when we have the acceleration, we've got n prime, a new fn prime, we have a new acceleration, or a new normal force, minus mg, it now is going to be equal to ma. This is not equal to 0, because here we had no acceleration. Here we have some acceleration. So now we can solve for normal force. So fn prime is going to be equal to m times g plus a. So we factor out. And this is larger than normal fn, right? So we require a greater normal force when we're accelerating. Okay, so now we've discussed normal force. We've discussed the y kind of component of this vector here, but now we want to discuss the frictional force. So friction, the magnitude of friction, magnitude of friction is going to be equal to some constant times the normal force. So it's proportional to the normal force. And this little constant of proportionality, called mu, is the coefficient of friction. And mu is in the dimensions of nothing. Mu is a dimensionless quantity. So you don't need to deal with any units. So the direction of the friction is going to be opposite to the direction of motion. So that should be fairly obvious because friction resists motion. So it's going to go in the opposite direction of your velocity. So we can find the direction of friction additionally by using kind of the unit vector notation. So if I have my vector over my magnitude, I can set that equal to negative velocity vector over velocity. So that makes sense that it points in a negative direction. But also, empirically, if you try to slide a book in front of you right now, well, the friction is going to go in the opposite direction as you're pushing. That should make sense. And we have two types of friction. We have static friction and kinetic friction. So the first is static, so mu s. So this is if I have a book, and I'm exerting a force on it, but it's not moving. So that's when the friction is static, because I'm not moving anything. I'm just pushing the book, or I'm pushing my hand against something, and it's not moving, but I can feel the friction resisting still. Then we also have kinetic friction, mu sub k, and that's when I am moving something and I am resisting a force and I'm feeling a force. So if I slide a book and the book stops, it's experiencing a force of friction. And we always have the case that the static friction is always going to be greater than the kinetic friction. The coefficients will be greater. Okay, now finally I want to discuss one more type of force, and this is to do with springs. So Hooke's law, we're going to talk about Hooke's law. So we are going to be looking at springs. So springs are actually very important in the world of physics because many things act like springs. If you take your pencil and you maybe hold it against the table, and then you bring a little bit off of the table, and then you like push down, or maybe this works better with a ruler or something. It's going to oscillate. It's going to oscillate a little bit, and that acts like a spring. And it turns out a lot acts like a spring, and that makes it very important because we can approximate a lot of things with these springs. So we will call a spring that's not subjected to any force, which would be at its natural length. We call that the equilibrium position. So if I'm at my equilibrium position, if my mass is at the equilibrium position and I have a spring here, and this is my mass, we call this x naught. And we can write that we have a special law for when we stretch our springs or relax our springs that says that the force due to the spring, or the force on the spring, is equal to some spring constant times the displacement that we move the spring. So if I move the mass to some x prime, then this is going to be delta x. Then I move the spring a little bit. Okay, so that's Hooke's law, and the Hooke's constant, K, is in the units of newtons per meter. All right, so that's all the three things I want to cover. Thanks for watching.